Hello everyone! In this video we will continue to examine topic 7.3, the structure of matter, and in particular we will continue to unpack Feynman diagrams. Alright, in the last video we examined how we can use Feynman diagrams to unpack all of the fundamental vertex interactions of quantum electrodynamics and then applied it to actual pair production and annihilation. As it turns out, there are many too many vertex interactions for the weak interaction for us to categorize them all. But what we're going to do is take a look at a number of different types and apply them to a couple of different situations. So the first vertex interaction we're going to look at is this one right here. In it, we have an electron scattering, okay, and in the process emitting a weak boson. Now notice that the electron comes in and the electron comes out, which means that the weak boson that has to be emitted at this particular vertex is the Z0 boson, or the neutral Z or Z boson. We sometimes describe this as a neutral current interaction, and that this sort of exchange particle in a more complex interaction is the neutral current. So far so good. But things get a little more complicated when we take a look at the emission of a weak boson that is not the neutral boson. In this particular case, we have a down quark. The down quark has a minus 1/3 charge, labeled here just for clarity's sake, and the down quark is going to emit a W- boson. Now, the thing is, the W- boson is negatively charged, which means that if it's going to do this, charge needs to be conserved at this vertex. And the only way to conserve charge at this vertex, because we start with only minus 1/3 of the elementary charge, is for this down quark to change flavors to an up quark at plus 2/3 charge. It could change flavors to another generation, but that is unlikely, as it turns out. So it happens to be becoming an up quark here, and we can see that the up quark with its plus 2/3 charge is plus 2/3 plus minus 1, giving minus 1/3 charge after the particle has interacted. Notice that the baryon number stays the same as well. So the baryon number plus 1/3 before the interaction and baryon number of plus 1/3 after the interaction. Notice that the W- boson has no baryon number, or has a baryon number of 0. All right, so that's one example of a weak interaction. Notice that this is an example in which quarks are undergoing a weak interaction. Recall that when we first introduced the elementary particles of the Standard Model, I was careful to specify for those particles which interactions they undergo. And quarks undergo all 4, so they can show up anywhere. But as it turns out, leptons do not. So leptons do not undergo the strong interaction, but they do undergo the weak interaction, and they can undergo the electromagnetic interaction as well. In this particular case, we have a negatively charged muon. Recall that the muon is like an electron, but it's in the second generation. And that negatively charged muon is again going to emit a W- particle. So the negative weak boson. This is what is known as a charged current interaction, in contrast to a neutral current weak interaction. Notice here that in order to conserve lepton number, this outgoing particle must be a lepton, but in order to conserve charge, that outgoing lepton cannot be a muon. And in fact, this muon transmutes into a muon neutrino. Notice that muon neutrinos are neutrally charged, thereby conserving charge at this particular vertex. So in general, there are lots of different types of weak vertex interactions. These are just a few, but take care. You will almost always need to use or want to use conservation of charge, lepton number, or baryon number in order to determine sort of a missing particle or to answer a question at these weak interaction vertices. Notice that the possible exchange particles for the weak interaction are the W plus and minus and neutral Z bosons. The range of these interactions is very, very short, so that's useful information as well. And every once in a while, they just straight up ask you for it. All right. In the next video, we will apply this set of understandings of the weak interaction to probably the single most important example that we will cover this section.